Okay, I'm gonna try this really quick and see how this goes. Okay. So the first thing we want to know for these kinds of equations are like, what are we going to pull from this? What is it asking us for, right? And we have a general understanding of what it could be asking us because we've only reviewed chapter 16, 17, and 21. So it's and it's going to be either on like thermodynamics, electrochemistry, and um, whatever chapter 21 was. I forgot what it was called. But yeah, so this is going to be chapter 17 stuff. And then one of the formulas we're going to want to know is uh, this is so weird. How do I more settings? Nope, I don't want this keyboard out. Okay. Is the Nernst equation. And the Nernst equation is basically the potential of the cell is going to be equal to the potential of the cell in standard condition minus the gas constant times the temperature over, this is going to be written as N for now, but sometimes it's also written as Z, times Faraday's constant, and then natural log of, oops, of Q, natural log of Q. Um, and this is the Nernst equation, and we're going to be using some form of this equation for most of the questions that have to do with chapter 17 at least. And it's just going to be a matter of what we're going to be rearranging to find what. And if we're looking for E of the cell, the potential of that cell, or if we're going to be looking for the potential of that cell in standard conditions, or if we're going to be looking for the equilibrium constant, which I'm going to explain a little bit of how it relates to this equation. So when it comes to this equation, we're going to simplify this, right? Because right now, we're not given temperature, and so we're going to assume this is in standard condition. So when it's in standard condition, our R will be 8.314, which is our gas constant. And then our F is going to be our Faraday's constant, which is 96485. Is it? What's Faraday's constant? I think it's 96485 or something like that. All right, let me finish writing it. 4, 8, 5. And our temperature, our standard temperature is 25 degrees Celsius, which is 298 Kelvin. Let me remove this real quick. Faraday constant, 9645. Yep, that's right. Okay. And because we're going to assume it's in standard condition and at equilibrium, this is going to be simplified. So when the cell is in equilibrium, E of the cell is going to be equal to 0. And so because it's equal to 0, we're going to rearrange this whole thing, and it's going to be E of the cell standard is equal to RT over NF natural log of Q. And when it's in equilibrium, Q, this is something we learned earlier on a couple chapters ago, is the reaction quotient. And when it's in equilibrium, it will be equal to K. So this can get changed out to K. So we're going to rewrite it one more time, just so we know what's happening here. Okay. And when this is all in standard condition, we're going to multiply these all out and divide it by that and keep this as an unknown. And the number we get from that is like 0.02 something. And then we multiply that by 2.303 if we want to change the natural log to log. So that's going to give us our basic equation with log instead of natural log. with log base 10. And so it's going to look like this now. Bye. 0.05916. I hope that's legible, over n. So that's with all of this multiplied and divided, multiplied by 2.303 to change this out to make it easier for us to log. Okay. Finally, this is probably going to be the formula we're given, but I just gave you like its origin story here. Okay, and so now what we're going to do is let's look at this question. For the following reaction, generate an equilibrium constant. So I assumed we've already read that, right? Since we're assuming equilibrium here. And calculate the numerical value for K, which is this thing we're going to find. Assume H, or the proton, is equal to 1 moles, 1 molar, given the following reduction potentials. Hint, balance this equation first. So what does this mean? We have this equation here. We're going to go through all of the steps to balance a redox equation. And then from that is where we're going to find our N, our moles of electrons. And from that, we're also going to determine which of these is our reduction and which of these is our oxidation. Okay, this can be the oxidation or this can be the reduction. We don't know. Sometimes we can look at the higher number and assume if it's a higher voltage, it's our reduction. But this is, I believe this is different because it's in standard conditions. So we're going to figure it out. Okay. I wish erasing was easier on this thing. How do I erase? This is so crazy. Do I just press? Okay, so maybe not. That's okay. I don't think this thing's capable of erasing. Okay, so step 1 over here in balancing this half reaction is to separate it into 2 half reactions. So step 1, we're going to separate it. We're going to have this. This is a 2. 0, 3, 2 minus aqueous plus Ta. See, I've already messed up because this is not, I'm just like trying to figure out how to work this thing. Step 1, we're starting from step 1. Good God. Okay. S, that's for one of the half reactions, and the other one is going to be Tas, Ta₂O₅ aqueous. Okay. And then step 2, we're going to balance everything except for oxygen and hydrogen. So we're going to balance this by adding a 2 here. And then we're going to balance this side by adding a 2 here. I have to rewrite the whole thing. Oh, I didn't realize it can close that. 2 BAS. And this one now is 2AS. Boop. Ta₂O₅ in your state. Okay, and now step 3 and 4 is going to be balanced. That 3 is going to be balancing the oxygens, and to balance the oxygens, you add H2O to the opposite side by however many oxygens you have on this side, so that way you can get that many oxygens on this side. Same thing goes for here. And then I'll just do it really quick. So we have 3 oxygens here. Maybe I'll exclude the states just for the sake of saving space. And then we're going to add 3 waters here. Good job. There we go. And then this side we have 5 oxygens there, so we're going to add 5 H2Os here. This is its state. It's a liquid. Okay. Then we're going to balance the hydrogens by adding that many protons or hydrogens to the opposite side. So we have 6 here, so we're going to add 6 protons here. I think I'm going to start excluding the state just for the sake of space. And then this side has it has 10 hydrogens, so we're going to add 10 protons onto that side. Oh, I did say I was going to exclude the state. It's just habit. Okay. Step 5, is going to now be to balance the charge. So we have a total charge of +4 here and a total charge here of 0. So we're going to, this is +4 or 4 plus. So we're going to add 4 electrons to the side of the equation so that it can get to 0 right now, because right now it's positive. So 4 electrons plus 6 protons. This is getting wonkier and wonkier. Okay. And then I feel like where am I? Did I ever add the 10 protons this side? Nope, I did not. They're right here. Okay, so this has 10 protons on this side and 0 on this side. So the charge on this side needs to have electrons added to reduce it to 0. So this is a 10 plus. So we're going to add 10 electrons to the product side. So let's write out the entire thing. Plus 10 protons. Hi. This is supposed to be on this side of it. I got too eager. Plus 10 electrons. Okay. And then step 6 is we want the electrons to be the same on both half cells or both half reactions. And so usually if they're smaller numbers, you could just like multiply this side by 4 and this side by 10. You'll get 40 electrons total. Then you're going to end up wanting to simplify or all that stuff. But you could do this a little bit easier. You can find out what numbers can you multiply both sides by to get the same number. So like if I multiply this entire thing by 5, I will get 20. And if I multiply this entire thing by 2, I'll get 20. And so we'll do that here. Electrons plus 30 protons plus this bit. Hope so. Okay, and this entire side is going to get multiplied by 2. Right? Yeah. That's just H2O. I accidentally clicked the button. Oh, wait. This is supposed to be 10 now. I'm not just copying down. This is supposed to be 2. This is supposed to be 20. And this is supposed to be 20. There. And then step 7, we add this entire thing up. And so we're going to like cancel what we have on both sides. There's 20 protons here, 30 there. So all of these can get canceled, but there will be 10 left over here. There's 5 of this, that's fine. 10 of this, that's fine. There's 15 waters here, 15 H2O, and there's 10 here. So all of these will be canceled out, and we'll have 5 left, I think on this side, right? Oh no, I think this becomes 10, 15 H2O. Yeah. Yeah. And then, but the number we want from here, we can balance this entire thing out, and add it all up together and write it out, but that's not what we want here. We've already got our answer here. Our answer here is the mole of electrons. That's the N that we need. And then something else we can look at too while we're here is which one is being reduced and which one's being oxidized. So here, barium right here, or Be, is -2 times 3, -6, and you have 2 of these, which makes these +2. Because you're left with a 2 minus charge. And then on the other side, it's reduced to 0. And then let's look here. Ta is 0. And then by the time it gets to the other side, oopsies. This is going to be -2 times 5, -10. And then this is +5. So then it goes up to +5. So this one is being oxidized. It's having electrons removed. So now we know this one is our reduction, and we know this one's our oxidation. And what's the equation for E of the cell? Well, it's right here. Let's take care of that right now. How do I get more space? Right here. So the equation for E of the cell is reduction, E of the cell reduction minus oxidation, or cathode minus anode. Let me go back up here. And so what we're going to do here now is E of the cell is going to be equal to -2.63 volts minus -0.75 volts. And so then our E of the cell is going to be equal to -1.88. Nice. So now we have our E of the cell, we have our moles of electrons, we have this number up here. The only thing we don't have is K. And so now that we have all of our numbers, all of our only unknown is K. So now we can plug it all in, and then it just turns into like algebra of rearranging the equation to find K. So let's, oh, how do I make more space? Let's do it over here. Yeah. Okay, so now we have -1.88 is equal to 0.05916 over, oops, this is known now as 20. That's this number right here, our moles of electrons. And then log of K. We multiply both sides by 20 to get rid of this one here. And we multiply this side by 20. And then we get -37.6. Then now that this, let's write it out. In class, I know he like cross multiplied it. But now to get this separated from log K, 916, we're going to divide both sides by 0.05916. Then we're going to get this big boy number equals log K. And then to get rid of base log, you just 10 to the log, boop, that gets rid of it. 10 to -635.56 is going to be equal to K. You can plug this into your calculator. Some people's calculators malfunction. Some people's calculators will tell you 0. It's actually just a really, 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 really small number. And so, yeah, I might say 0. But he is okay with this answer on the exam. If it gives us 0, he is also going to be okay with seeing this answer on the exam. And that is how you answer this question using the Nernst equation. It might be helpful to reread chapter 17 and find all the ways you can rearrange this equation to get the numbers you want, and to understand what is being asked in the question, and what's given to you, and how to take that to get the answer you need.